Okay, so we're going to start. I would like to remind everyone, as you probably already know very well, we are recording this session. So if you would like your image not to be recorded, please turn off your camera. Then the second thing is there is a transcript at the bottom of your screen, possibly. If you find it annoying and would like to turn it off, there is an option to do that. At the bottom, there is a button that says share screen, and then next to it is, at least in my version, there's a button which allows you to turn off the live transcript. So we have one speaker today, and this is Dr. Ben Withers from the University of Southampton, who is the author of a number of well-known papers on black holes, ABS-CFT, and hydrodynamics, and in particular relevant to the subject of our meeting, he wrote a very influential paper which somehow focused some of the research on the hydrodynamic gradient expansion on studying properties of the dispersion relations of linearized perturbations. So without further delay, Ben, please go ahead.
Thank you, Michal. That's very kind of you to say those things as well. And let me also thank Ines and the other organizers for inviting me to be a part of this Hydro Focus Week. Yeah, so my talk is from quasi-normal modes to constitutive relations. And, oops, yeah, okay. So the focus, let me just check. You can see my cursor, can you?
Yes.
Okay.
Yes.
So the focus of this talk is just on classical relativistic hydrodynamics. So we're not going to consider any of the sort of stochastic or late time power law decay that we may have discussed in the sessions yesterday. So it's just classical relativistic hydrodynamics. And when I say hydrodynamics, what I really mean is phrased as a gradient expansion. So it's an effective theory which is constructed order by order in gradients. And in special cases, which we heard about a lot on Tuesday with Michal Heller's talk, when you look at symmetric flows, in particular the Bjorken flow, we're able to compute properties of the hydrodynamic expansion to very large orders. And this case is by now quite well developed, and we understand the structure of trans series and so on that appear there. So in this talk, I'd like to talk more generally about the large order behavior in classical relativistic hydrodynamics. So not just focusing on the Bjorken flow, but looking at things which don't have the same types of symmetries. So this covers developments that I would say have emerged over the last approximately 3 years. And the three rough areas are quasi-normal modes, constitutive relations. So quasi-normal modes is very much the realm of linear analysis. So you take the hydrodynamic equations and you linearize them in amplitude. Within that linear analysis, we can also look at constitutive relations, and then we can ask about the more general nonlinear problem. So this is roughly the activity over the last 3 years that I would like to try and summarize for you today in this talk. Give you some of the key results and hopefully extract some general lessons and some open questions which we can try and discuss in the sessions tomorrow as well. So the nonlinear problem that I mentioned in this third point, Alex Cervantes will be discussing that in his discussion tomorrow. Okay, so the outline of this talk is split into part one, which is quasi-normal modes, where we'll be talking about the dispersion relations of quasi-normal modes and their convergence properties. Part two will be relating these properties to the large order behavior of one-point functions of stress energy tensor through the constitutive relation. And part three will be a very much specialized example where we'll simplify as much as we can in order to get as far as we can in terms of writing down closed form expressions for trans series in the case of diffusive physics. And I'll end with a summary in open directions. So let's start with quasi-normal modes. So as we heard from Michal on Tuesday, hydrodynamics governs the conservation of currents near thermal equilibrium. So here I have the the current corresponding to the stress tensor, so this includes energy and momentum conservation, expressed as this following conservation law: divergence of the stress tensor equals to 0. And hydrodynamics is organized as an effective theory where we expand in derivatives of hydrodynamic variables. So in this case, for just conservation of energy and momentum, we have the corresponding hydrodynamic variables, which are temperature and a fall velocity. And based on knowing that T mu nu has to be constructed out of these variables and their derivatives, we can construct a constitutive relation. So T mu nu is typically written as an ideal part, which contains T and U, but no derivatives of them, and a pi mu nu, which contains all the derivatives. So this is usually referred to as the dissipative piece. So pi mu nu, you can organize that based on how many derivatives appear in each of the terms. So you can express that, if you like, in a formal way by saying you sum over all the possible tensor structures that are allowed to appear by symmetries. These tensor structures are built from U, T, and their derivatives. And you can attach to them some formal parameter lambda, which simply counts the number of derivatives that appear in an expression. So at n equals 1, this would be a term with one derivative. So in relativistic hydrodynamics, for example, at n equals 1, there's two possible terms that appear. There's the shear tensor, the shear viscosity term, and the bulk viscosity term. And this is basically just bisymmetries. So what about quasi-normal modes? So this is perhaps not the language you would usually encounter in this hydrodynamic context, but we'll see later why I'm calling them quasi-normal modes. So these are basically just excitations of the system around thermal equilibrium. So we take these equations of motion, so we take this constitutive relation and we plug it into this conservation equation, and that gives us a set of equations of motion for these hydrodynamic variables. So they're just classical partial differential equations. So if we linearize these partial differential equations around thermal equilibrium by taking perturbations of this type, we say that temperature is a constant plus a plane wave and the velocity in a similar way, and we take a plane wave with momentum k and frequency omega. We plug this into the equations of motion and linearize, we find that solutions only exist when there are specific relationships between omega and k. And these are the dispersion relations. Now, since we constructed this constitutive relation order by order in gradients, the corresponding dispersion relations are also constructed order by order in gradients. So the way that these are traditionally presented is to write the frequency as a series in small spatial momentum k. And there are two different types of mode you can find in this hydrodynamic context. One of them is the sound mode, which propagates at the speed of sound, and one of them is the shear mode, which is diffusive. One thing you'll notice about these modes is they both share the property that the frequency goes to 0 when the momentum goes to 0. So this is what I will be in later slides calling a hydrodynamic mode. So if it has this property, I'll be calling it hydrodynamic. And the reason this is significant is because when k goes to 0, you have something which doesn't depend on time. It's a conserved quantity, and these are the conserved quantities associated to this conservation law in the first place. So the existence of these sort of hydrodynamic modes is linked to the existence of conserved quantities. So these are very special. So that's quasi-normal modes for relativistic hydrodynamics. Let's discuss a different case, which is not hydrodynamics. Let's discuss a class of theories, which Michal also introduced on Tuesday, which we'll call holographic quantum field theories. So traditionally, these are conformal field theories. And in holography, holography tells you how to compute correlation functions in these special quantum field theories by doing calculations in classical Einstein gravity in one higher dimension. And in particular, it's one higher dimension with a negative cosmological constant. So the solutions have asymptotically ADS spacetimes. And in addition, if we want to look at a thermal deconfined state in this quantum field theory, this is described by a black hole in ADS. So this is just a convenient way of doing calculations in these holographic quantum field theories, which are strongly coupled, by just doing a gravity calculation. So the analogous quantities to what we computed on the last slide, these quasi-normal modes, is to just linearize perturbations of the metric around this black hole space-time. So those of you who are familiar with general relativity will recognize this is a portion of the conformal diagram for Schwarzschild black brane in ADS. There's a future event horizon and there's a conformal boundary. So you take the metric and you linearize around this Schwarzschild solution, and again you pick plane waves on the boundary directions. So these are the field theory directions, and each of those plane waves comes with a radial function. So what you end up with is a set of ordinary differential equations as a boundary value problem. You have a condition, a physical boundary condition at the horizon, a physical boundary condition at the conformal boundary, as dictated by the problem you're solving in the quantum field theory. And once you've solved this boundary value problem, you find a set of frequencies, omega of k. So these are the quasi-normal modes. So there are actually infinitely many of them. So as you might imagine, when you have an ordinary differential equation with some boundary conditions, there are these infinitely many solutions to this problem. And even though there are infinitely many, we can still try and classify them in their behavior at small momentum. So these were exact in k. You can construct these at any finite k you want. The theory is perfectly sensible for any k you would want to pick. But in particular, you can look at them at small k. So if we expand them for small k, what you find is that there are two modes which are hydrodynamic in the sense that we introduced before, in that their frequency goes to 0 as k goes to 0. And that's again because even in this context, you have those symmetries, those translational symmetries in space for momentum conservation and translations in time for energy conservation. So these modes have to be there. In addition, you have infinitely many more modes which don't have this property. So when you take k goes to 0, you'll find frequencies which are, people say, are gapped. So you might write this as a negative imaginary part with some time scale tau. So these are modes I will refer to as non-hydrodynamic, transient modes. So these are modes which did not appear in the hydrodynamic calculation we did on the last slide. These are not part of any hydrodynamic theory. So we have hydrodynamic modes, and we have infinitely many non-hydrodynamic or transient modes. So we have quasi-normal modes in hydrodynamics, and now we have infinitely many quasi-normal modes in a microscope, let's call it a microscopic theory, which is this holographic quantum field theory. How can we tie everything together? So I'm going to draw this picture. So in this bubble representing hydrodynamics, we can get there by taking a microscopic theory in this other bubble, and that might be one of these holographic quantum field theories we just looked at with ADS gravity. It could be some theory that's MIS-like, Muller-Israel-Stewart-like theories, which we've discussed in previous talks, such as BRSSS. It could be kinetic theory, it could be QCD, or whatever your favorite microscopic theory is. So these theories contain not only hydrodynamic modes, but non-hydrodynamic modes. So to get to hydrodynamics, you basically have to integrate out all of these extra modes, these heavy degrees of freedom, and then gradient expand the result. So this is like a matching calculation in an effective field theory. An example of this in practice for the holographic story is what's known as the fluid gravity map. So this gets you from a microscopic theory to a hydrodynamic theory. And of course, there are many different microscopic theories which get you to the same structurally hydrodynamic theory. The only difference is the values of the transport coefficients. And then we said, if you want to compute quasi-normal modes of the hydrodynamic theory, we just linearize these hydrodynamic variables, the temperature and the velocity, and we find these sound and shear modes. We also looked at, on the last slide, linearizing gravity in this holographic quantum field theory example. And again, these were plane waves, and we found infinitely many frequencies. So what's the connection between these two? Well, it's just the matching. So you would gradient expand these for small k. You would have infinitely many expressions which have a small k expansion, but only some of these have the requisite property to be hydrodynamic modes. That is to say, whose frequency goes to 0 as k goes to 0. So in going from here, from this left bubble to this right bubble, you would discard all of the non-hydrodynamic or transient modes. Related to a conversation we had yesterday, note that these particular non-hydrodynamic modes are physical. They're real physical excitations of the microscopic theory, which are not described by the hydrodynamic effective theory. They're outside the regime of applicability, if you like, to say it naively. And these should be distinguished from the modes you would get if you were to take hydrodynamics to a certain order, truncate it, treat that as an exact theory, and then compute the quasi-normal mode spectrum. So my argument would be, as soon as you truncate hydrodynamics, you're really going back up to a candidate microscopic theory, and that might not be a sensible or well-defined microscopic theory. And that's the case, as we understand it, with first-order relativistic hydrodynamics. So that's sort of my broad overview of quasi-normal modes. So I think it would be a good point if there are any questions about it. Now would be a good time.
I have a minor question here.
Yeah, hi.
So, hi. When you say this, you are talking mostly about, at least the examples that I have seen are in holographic, but for instance, in weakly coupled systems, how does this picture hold?
In other
words, how do you do this summation over the frequency? Because over there you have to do something a little bit more subtle. That's my worries.
So the weakly coupled theory I know of would be, let's say, kinetic theory and RTA. And then you would have a Green's function. And so these quasi-normal modes, I've just talked about linear response. And so these quasi-normal modes also appear as poles of two-point functions of these currents, right? So the stress tensor 2-point function, or the Green's functions that you compute in, let's say, kinetic theory, would contain poles at these.
You have also branch cuts.
Yeah, so that theory is more intricate. Yes, absolutely. So I've absolutely glossed over those issues. So these theories are, for the most part, all very nicely behaved. So these holographic theories, the MAS-like theories, they're nicely behaved theories. Yeah, indeed. In kinetic theory, you have a branch cut in the Green's function itself. And yeah, so I'm just not discussing that.
Okay, thank you.
Yeah, I have nothing useful to say about that case.
Thank you.
But you also have these poles, and they can interact with that branch cut. So you can have collisions of these poles with the branch cut.
Yes.
But anyway.
Thank
you. Good. Any other questions?
Yeah, so to what extent can I ignore the word relativistic? Is it Boltzmann transport in the top and ordinary Navier-Stokes at the bottom?
Sorry, could you repeat the question?
To what extent can I ignore you when you use the word relativistic? So can I start with Boltzmann transport equation top left and go down to Navier-Stokes, compressible Navier-Stokes on bottom right?
I would, well, okay, so when you start with, yes, so I think that's probably in spirit, that's true. Now, I don't know to what extent these specific statements I made in the intermediate stages are correct, but I think, yes, in spirit, that would be the case. So you'd have some microscopic theory, and then you'd have some long wavelength near equilibrium theory like Navier-Stokes plus corrections, and there would be a matching calculation between those two things, which determines the transport coefficients. Yeah. So I think they would all fall into that pattern if we are to treat hydrodynamics as an effective theory. It's just I'm only talking about relativistic in this talk just as a matter of the scope of the talk. But yeah, I think more generally it's the case.
Thank you.
Any more questions? Okay, so that completes the summary of quasi-normal modes, at least what they are. The next step is sort of to compute some in actual models. So what we're going to do is take one of these holographic models. In particular, this is a model which has Einstein-Maxwell theory in four space-time dimensions in asymptotic ADS. So this is a resurgent black hole. And we're just doing that calculation I mentioned. So we're doing a linearization of the metric, and we're computing the spectrum of quasi-normal modes. So this is what you get. Here I've plotted the imaginary part of the frequency of these modes against the momentum. And as advertised, there are many of them, and this plot just goes down the imaginary frequency axis seemingly forever with infinitely many of these modes appearing. And as we discussed, in this sector is the shear channel. So in this shear channel, we have the shear mode. So as discussed, there is a mode whose frequency goes to 0 as k goes to 0. And this is the hydrodynamic mode. In addition, there are infinitely many other modes whose frequency does not go to 0 as k goes to 0. And these are the non-hydrodynamic or transient modes. But you can see that already on this plot, something very interesting is happening at this point, at k of roughly 1.2. These modes are colliding with each other. So as I increase k, they come closer and closer together, and then they turn into this pair of complex modes. So this right here is a square root branch point of this function appearing in this function omega of k. So immediately you would conclude that this would be an obstruction to the radius of convergence of this hydrodynamic series. So you would not expect the hydrodynamic series to converge past this singularity, which is a branch point. But in fact, there are other branch points, and the way you have to look for them is to look in the complex k plane. Of course, what you want is the closest singularity to the origin, and that will set the radius of convergence of this hydrodynamic series. And so for that, you have to look at complex k. So this is the first question we want to answer. This hydrodynamic expansion governing the dispersion relations, what is the radius of convergence? So for this model, one can compute these coefficients, omega n, to some relatively high order. So I computed them to roughly order 80 in the hydrodynamic expansion. And then you can just look at their convergence properties. So here, what I'm plotting in this top plot is basically a ratio test. So it's 1 plus the ratio of these two successive coefficients. And it shows that ultimately this series converges with a radius of convergence given by the scale k star. K star is set by some thermodynamic quantities and the shear viscosity. So that you can see by doing this ratio test. You can also see it if you want by doing a Padé approximant of this series and branch points that appear in a, if you do a Padé approximant of a function which contains a branch point, you will see those as an alternating series of poles and zeros. And that's indeed what you see. So when you do a Padé approximant of this series and plot it in the complex k plane, you see that there's a singularity occurring at this scale k star and a branch cut emanating from it. So let's plot now, instead of before we plotted along the real k axis, let's plot it along the imaginary k axis. This is what the dispersion relation looks like, the exact dispersion relation. Since we have the microscopic theory, we can just compute the exact dispersion relation. And these are in, this is given in the black points. So we can see that there's this hydrodynamic mode or sheet, which goes to 0 as k goes to 0. And as you increase k, the imaginary part of k, then you reach a branch point singularity at k star. So this, in the literature, in the holographic literature, is usually referred to as a mode collision. But in the mathematical sense, it's a square root branch point. So as a result of this singularity, if you try and just plot on top of this curve, the hydrodynamic approximation to the dispersion relation, so you just literally take this partial sum over 80 coefficients of k to the n, and plot it on top, you get the green line. So of course it converges nicely up until k star, and then it disagrees. And no amount of adding more terms will improve that beyond this point. So this radius of convergence seems to rely on the existence of this non-hydrodynamic mode. If this non-hydrodynamic mode wasn't there, there wouldn't be this sequence of collisions. So given this partial sum, there's a question of whether we can do better than just simply adding up these numbers. Of course, the usual way you would do that is with a Pardee approximant. But we know it's slightly more than that. We know that there's a square root branch point near k star. So we can try and play a game with that. Instead of using k, we can switch to a new complex variable z, which mimics the structure of the branch point near k star. So we'll subtract I k star from k, which is the location of the branch point, and we'll equate this to z squared. So in a sense, this is undoing the square root operation and turning two sheets into one. So this z variable should cover more than one sheet. So we take this partial sum, we plug in this new k variable, and now we have an expansion in z. So now it's a sum over coefficients in a series in z. We can then do a Pardee approximant of that new series, and then undo again the transformation from k to z and go back from to get back from z to k. So going back from z to k introduces a branch. You have to choose which sheet you go on, and if you choose the second sheet, then what you do is you recover the non-hydrodynamic mode. So this is a table of the values of the frequency you recover by picking the second sheet when you undo this transformation as a function of a number of orders you keep in the hydrodynamic expansion. So by order 80, this process recovers, to 4 significant digits, the frequency of the non-hydrodynamic mode. So pictorially, what we've done is go from a simple partial sum of the hydrodynamic expansion through this change of complex variable and Pardee approximation. We've generated these two sheets, this green sheet and this green line and this purple line. And you can see very well that it agrees nicely with the exact result. And in particular, this purple line goes back to k equals 0 and extracts the non-hydrodynamic mode. So in other words, by a suitable sort of resummation of this hydrodynamic transport coefficients, this hydrodynamic series data, it's possible to extract some information, some detailed information about the non-hydrodynamic modes you integrated out in the first place to get to hydrodynamics. And I think if you had enough terms in the hydrodynamic expansion, it would be possible to continue this indefinitely, and you could use this branch point to continue this procedure and go to the next sheet and so on. So it seems reasonable to suppose that all the information about the microscopic theory is really encoded in some rather obscure way in the hydrodynamic series data. So one can also look at these branch points as a function of some parameters. So this was work by Aaron Janssen and Cristiana Pantalidou. And what they did was vary the amount of charge of the black hole. And you can see that the branch points undergo, have their own trajectories as a function of charge. So this blue line was the branch point we looked at over the last few slides, and it has its own trajectory. And at some point, it exchanges dominance with a different branch point, which is this red line. So obviously, the radius of convergence is set by the closest one to the origin. So as you dial this parameter, you just have to keep track of which one is closest. So this critical value of the charge, this red one takes over. And there's quite a lot of work understanding these branch points in other theories over these last 3 years. So we have Rice and Nordstrom, which we just discussed. We have Schwarzschild. There are near-extremal examples, kinetic theory, what happens if you turn on magnetic fields, Einstein-Gauss-Bonnet gravity, magnetohydrodynamics. So there are lots of pieces of evidence that the square root branch points set the radius of convergence of this hydrodynamic series across a wide variety of models. There's also examples which are not square root branch points. So in this case we just looked at, where you're allowed to tune the charge. If you tune the charge just right, you can have two branch points square root branch points coming together to form a quartic branch point. So this was something that was observed in this work. And in kinetic theory, as was alluded to earlier, kinetic theory is just a little bit more complicated because there's a logarithm appearing in the Green's function. And so you can have what that translates to in terms of the radius of convergence of the dispersion relation in some cases, it's set by the existence of a logarithmic branch point in omega of k. There are also essential singularities that appear in omega of k, but they don't turn out to set the radius of convergence. And there was some discussion about these branch points yesterday in Matteo's discussion section, which was actually a lot of fun. So I recommend you check it out. So we have a fairly consistent picture of what's going on, which we can summarize as, we have multiple branches of some complicated Riemann surface, omega of k for k in the complex plane. The radius of convergence of the hydrodynamic series for the hydrodynamic modes is set by the closest singularity to the origin and on the appropriate sheet. And this is something you can call a mode collision, or has been called a mode collision. And in reality, it's a square root branch point singularity across many examples.
Ben, can I ask a question?
Yes, please.
Yeah, so if you only know the hydrodynamics, is the nature of the mode collision an additional new information you have to supply, or is it something that somehow it's also secretly encoded?
So this, for example, this plot here, so this is a plot of the complex, so it's supposed to be K. It's a plot of the complex K plane using only, so in this paper, I was quite careful to use only the series data where possible. So I took the hydrodynamic series data, so these omega n up to n equals 80 or something, or 40, so that K goes to 80. And this plot you can make from only those coefficients. So you can see that at I K star, which is here, you see there's a singularity and it's a branch point. Now, I think you can, by looking at the slope, how quickly this converges, this ratio test, I think that tells you about the degree of the branch point. So you can, I think you can infer it all from this series data. And then once you have it, you can do that, you can try and do that resummation thing that I did, where you change variables to a complex, to a z squared, which unwraps this.
So if I was to take this more philosophical point, do you think the hydrodynamics part really encodes everything about the microscopic theory in some?
Well, yeah, that seems to be at least the quad. Well, yeah, okay. So this is linearized. At least all the quasi-normal mode frequencies, I guess. I mean, this example I showed, it's not particularly systematic. It's just I did what I could to get it. I would love to see a systematic way of doing this. But this really, to 4 significant digits here, it recovers that first quasi-normal mode. And I don't know to what extent the accuracy to which you can recover this degrades as you want. If I want to go to sheet 3, sheet 4, how many more orders in hydrodynamic series do I need? But in principle, I don't see, it looks already pretty good that that's the case. I mean, we know effective theories, this is an effective theory predicting its own demise, right? From the effective theory itself, we compute the radius of convergence. So I'd like to believe that if we had something like, let's say we had the first 10 terms in corrections to GR, right? R squared, R to the cubed, R to the 4. I'd like to think we'd be able to compute like the mass of like some Planck mass size thing to some better than just saying, we usually estimate that and say just on basis of scales, we think it's roughly the Planck mass. But this is, the answer here would be we think it's roughly order 1, but you can do much better than that. We've got 4 significant digits. So I'd like to think this would hold in any effective theory, even in quantum field theories. But I don't have any evidence to support that claim.
Okay.
Yeah. May I contribute a word to this discussion?
Yeah.
Sorry, the point is, I believe if you have, of course, infinitely many coefficients omega n, so you expand to arbitrarily order, when you provide infinitely many informations, pieces of information, so that is effectively contains all the information about all quasi-normal modes. And in principle, you can build an effective hydrodynamics which includes all gapped modes as well. So actually, I have been doing it for like 15 years nearly. Okay. So it's not a surprise, but if you can restore gapped mode, but if you have enough information about omega n, still you kind of UV complete your hydrodynamic theory by including infinitely many poles, but you are not back to microscopic theory. It's still an effective theory because it's essentially theory of a conserved current, which is stress tensor. So you may have degrees of freedom, microscopic degrees of freedom, which are not coupled or connected to stress tensor. This you will never see by studying quasi-normal modes only. So yeah, you cannot recover Lagrange.
Okay, but I think, yeah, I mean,
even if you know everything about omega k expansion of your stress tensor, that's what I believe.
Okay, okay. I mean, okay. So I mean, I would just say, yeah. So the most conservative thing I would say is that, you know, usually you would estimate when an effective theory would fail just based on the scales that appear. And this is just an example where you can do a lot better than just estimate at the scale. You can put some numbers to it, at least for the first mode. Yeah, so I think that's definitely a very interesting area. I would like to think more about that.
Ben, can I also ask a question?
Please, George.
So it's just that, so if you were to consider different equilibrium states, something that is moving with some constant velocity,
okay, yeah.
we know that even, you know, in the sound wave, a sound wave gets skewed because of, you know, the constant velocity is different than zero. So my question is, all the crossings in all these different points, of course, they would change where they happen in the omega and k space, but can you say that, you know, the crossings, then at least the number of crossings or how many of them can happen is a Lorentz invariant quantity? I mean, which would not depend on the equilibrium state. What can you say that is truly a Lorentz, like a scalar, a Lorentz invariant thing?
Yeah, I don't know the answer to that. I think, yeah, as you say, the way to view it is you have complex omega and you have complex k, and, you know, historically what people would be interested in is looking at real k complex omega, which quasi-normal modes. But if you want to now boost that, then you're really tilting that plane and you're asking about a different slice of that four-dimensional complex space. And I don't know on different slices how the singularity structure changes. Yeah, it's a good question. Yeah, I'd like to know the answer.
Okay.
Yeah. All right, good. So that was basically the final summary of the quasi-normal modes. And now what we wanted to go on to is the stress tensor. So actually, yeah, so we want to go on to constitutive relations. So if you recall, we would like to construct, so the constitutive relation expresses the stress tensor in terms of the hydrodynamic variables, the velocity, the temperature, and their derivatives. And there's a conservation equation. So now if we compute fluctuations about equilibrium using this system of equations, we get the hydrodynamic frequencies. So obviously, based on the fact that we can derive one from the other, the constitutive relation and the frequencies have an intimate connection. And because we now learned something about the large order behavior of frequencies, which might be generic, but we saw it in many examples of this, you have these branch points, we can use that to learn about the large order behavior of the stress tensor because of this connection. And in fact, in linear theory, what we showed in this paper is that there's an explicit map between the two things. So this is work with Michal Heller, Alex Sorantes, Michal Spolinsky, and Victor Svensson. So I'll just detail this now. So what we do is write down the most general constitutive relation for linearized conformal hydrodynamics. And there are basically only three terms that can appear. There's a shear tensor, which is given by this quantity here, derivatives of velocity. There's a traceless operator acting on, a derivative operator acting on the energy density, and a similar one, traceless derivative operator acting on the divergence of the velocity. This is one derivative, two derivatives, three derivatives. And these are the only tensor structures that can appear. And to each of these, we can increase the number of derivatives appearing just by acting on these with the spatial Laplacian. So in general, there's an arbitrary number of terms with different spatial Laplacians applied to them, which we're representing here by A of the Laplacian, B of the Laplacian, and C of the Laplacian. And where A, we mean sum over AN with that, the nth power of the Laplacian. So these ANs the transport coefficients, and similarly for B and C. So this is the most general thing you can write down. And now we can do a matching. So if we just simply count the number of transport coefficients appearing at each order, that's simple to do. It actually matches the counting of coefficients that appear in the series expansions of shear and sound modes at small k. So in fact, there's a one-to-one connection between the two, between these ANs, BNs, CNs, and the coefficients of k appearing in the shear and sound modes. So they can be mapped to each other. So let's take the AN as an example. So this function A was a sum over ANs with n powers of the Laplacian. These coefficients AN are just given by the coefficient of k to the 2n plus 2 in the shear mode. And then there are similar expressions for B and C relating shear and sound. So in other words, this is a matching calculation in the sense that if someone hands you a microscopic theory and says, okay, the shear and sound dispersion relations are these functions, then you can immediately write down the all orders constitutive relation for that theory, because you can just extract these A's, B's, and C's, and then you have it. So that's the first step. So now for simplicity, let's consider this example restricted to a shear perturbation. So we just take a perturbation of the velocity which is shearing. So this reduces that constitutive relation from A, B, and C just down to the A terms. And what we have is a sum over the A terms with powers of the derivatives, 2n plus 1 powers of the derivatives, acting on this shear mode function, U1, this shearing part of this velocity perturbation. So now we want to take this constitutive relation and do a convergence test. So we're going to apply the root test. So we'll take a term, the nth term, the absolute value, raise it to the power n, and take the limit. So this is the root test. And we want to check where this is below 1 for convergence, above 1 for divergence. But we know a lot about these things. We know a lot about AN, right? We know that AN has to be the coefficient of k to the 2n plus 2 in the shear dispersion relation. And we know the shear dispersion relation has a branch point, a k star, or at least we think it does from all the examples we've looked at. And so then we know that the large order behavior of AN to the 1 over n is actually given by the large order behavior of shear, which is governed by this branch point. So actually the growth of AN is given by 1 over k star squared, where k star is the location of the branch point. So that covers this piece of the expression. The second piece of the expression is the derivatives acting on the velocity. So now if we assume that this velocity perturbation is a square integrable function, which is compactly supported in momentum space up to some maximum momentum, that is to say we have some physical solution where the momentum is cut off at Kmax, so it doesn't have any more momentum than that. Then by the Paley-Wiener theorem, we know that this has to be an exponential a entire function of exponential type Kmax, which means that this limit gives us Kmax squared. So if we put those two things together, we can evaluate this C, this root test, and we find it's Kmax over k star squared. So in other words, if we limit the amount of momentum appearing in the solution to be less than the radius of convergence of the dispersion relation, then this stress tensor is, the hydrodynamic expansion of the stress tensor is convergent. And if we have momentum which exceeds that, then it's divergent. In this linearized context, if we restrict it to functions of compact support in momentum space, then this will be true for all time. So we can evaluate this on any time that we like. For example, the initial data, or we can evolve it to t equals 1 and evaluate it there. The result won't change. So this is valid for all times. And in specific examples, we observe that if we have functions of unbounded support in the momentum space, so all the way to Kmax goes to infinity, then what we find is factorial growth. So to summarize that, the convergence of the stress tensor in position space for linearized hydro, if we have some Cauchy or initial data compactly supported in momentum space up to Kmax. If Kmax is less than k star, it's convergent. If it's greater than k star, it's divergent with a geometric growth. If Kmax goes to infinity, it's divergent in a factorial way. And K star was this intrinsic microscopic scale. So someone hands you a theory, you can also compute Kmax for that theory, but then to answer the question about whether T mu nu diverges or not, you have to evaluate it on a solution and tell, because that tells you what Kmax is.
May I ask you something here? I just got curious about something.
Sure. Yep.
A quick question. So, how much this statement changes, for instance, in situations where fluid is expanding?
So this is linearized around thermal equilibrium.
But you can do, at least in kinetic theory, you can do the same when the system is expanding around an non-equilibrium background.
So that analysis is not covered. That case is not covered by this analysis. It's really dependent on. So, for example, the structure of the stress tensor, this most general constitutive relation that we wrote down, that relies on having no trivial background, a thermal equilibrium. So if we had other background dependence, we could have changed that by changing the functions that appear in that constitutive relation. So I think there's none of this applies to that case.
Okay, thank you.
At least on a first glance. Yeah, thanks. Yeah, so this is seemingly a world away from, let's say, Bjorken flow. But nevertheless, it is a world away from Bjorken flow and expanding plasmas, but we didn't have those symmetry requirements, right? This is an arbitrary linearized system around thermal equilibrium with no requirements of symmetry on the perturbations. So that's the advantage that we gain. So we can view this as a precise version of this law you might have heard every so often, that hydrodynamics breaks down when gradients become large. This just says, well, it's really whether when you have momentum in the system greater than this branch point momentum, K star. The other point to make is, of course, in this linearized context, we only have up to 2 transport coefficients each order. So this is not like the nonlinear case where the number of transport coefficients can grow at every order in the gradient expansion. There are really only 1 or 2 at each order. And yet this thing can diverge, right? So the divergence cannot be attributed to a growth in the number of transport coefficients. In fact, here the growth is attributed to just acting with a large number of derivatives on the data. So you take some data and you keep acting over and over and over again with these derivatives, and you do it a large number of times. And whether it diverges or not is just dependent on how that function behaves. And here we saw through the Paley-Wiener theorem about how to control that. So let's talk quickly about nonlinearities. So in some work that will appear hopefully shortly, and as to be discussed by Alex Cervantes in the discussion session tomorrow, we can do something with nonlinearities. So let's take MIS as our favorite toy model. MIS contains an evolution equation for the dissipative part of the stress tensor, like this, which demands that it evolves towards the shear tensor. So to evaluate the constitutive relation, all we have to do is basically invert this operator and act on this expression with it. So we move this operator from the left-hand side to the right-hand side. And this we can do if we're expanding in gradients, right? So you imagine a small number appearing in front of this differential operator, calligraphic D. And when we invert this, we're just getting powers of D acting on the shear tensor. So the nth derivative term in the constitutive relation is given by n-1 powers of this co-moving Val covariant derivative acting on the shear tensor. So this we can just evaluate. So you just take a solution to the MIS equations of motion in, let's say, 1 + 1. So here is an example of what the temperature does for some Gaussian initial data. You take the solution. With this solution, you can construct this derivative operator D. You can construct this shear tensor, and you can just simply compute these quantities. So you just act with D n times, and we do the root test, and you see it grows factorially. So here's an example, which is 1 + 1, doesn't have any of the Bjorken flow symmetry type results, but it in fact diverges factorially, just like Bjorken flow does. So this generalizes those kinds of results to 1 + 1 without symmetry. Another interesting observation about these solutions is obviously to compute this numerically, we have some numerical lattice, right? So there's a maximum momentum that can appear in this grid. So just like in the linear theory, we saw maximum momentum can cause convergence. That can happen here too. Because it's on a lattice, you'll find that the large power of this operator is given by the largest eigenvalue of this operator. And that's on the lattice is given just by the lattice spacing. So in other words, this curve, if we were to plot it for larger and larger values of n, would turn over and saturate to the largest eigenvalue of d. And that's basically the analog of k max that we saw for the linear theory. So in other words, by working on the lattice, it's possible, even in the nonlinear case, to arrange for the hydrodynamic expansion to converge by, again, the same physical mechanism. We just limit the amount of momentum that appears in the solution. Okay, so that concludes.
Sorry, can I ask a question about this? So there is a u mu inside of this d, right?
Yeah, there is. Yeah.
Yeah, and so I'm assuming that you computed the full solution, so you know the flow everywhere, the exact flow velocity. Then you can compute the exact sigma.
Exactly. So we compute. So it's a numerical exercise. We have this lattice, which is like periodic in x, just because it's easier, and some interval in time. And it's like whatever 400 by 1,000 grid points. And we compute. You can compute the velocity field everywhere. You can compute the temperature everywhere. And that allows you to compute everything in these expressions. So sigma, you can compute it. D, you can compute it. As you say, it contains the velocity. And tau, tau contains the temperature. And eta contains the temperature, and so on. So you compute everything exactly numerically on this lattice. And we checked, you can make checks that you might be worried, taking large powers of an operator, but you can check this converges. This factorial behavior converges as you go to the continuum. It also converges as you increase the precision that we're using.
Okay, thank you.
Yeah, so Alex will discuss this, I'm sure, in some gory detail tomorrow. Any other questions about what I've discussed so far? I have one part left, which is this example for diffusion, and yeah, maybe I'll go on to that. So the goal here is really to try and get as far as we can in terms of the resurgence language. And so we simplify everything as much as possible, essentially. So if we consider diffusive process, so that's characterized by having a mode which goes like this. So it goes like omega goes like k squared with an I. So in general, if you have a theory which has this exact dispersion relation, this will violate causality. And in any causal theory, there must be corrections here. So it's really k squared plus dot dot dot, and these are higher orders in k. But this leading term has a scale symmetry, which is you scale omega by epsilon squared and you scale k by epsilon, right? This is this diffusion is a fixed point of that scaling. But these corrections don't. So these corrections will appear with higher and higher powers of epsilon. The more and more powers of k there are, the more powers of epsilon there will be. So these are like the weights under a lift shift z equals 2 scaling. So we can use this organizational structure to try and construct a trans series in a quantity epsilon. And the way we do that is by taking the equations of motion and introducing this formal parameter epsilon by scaling time and space in the following way. And then we expand in epsilon, small epsilon. So the simplest way you can do this is by looking at the shear channel in MIS, linearized, and this is governed by the telegrapher's equation, which I'm writing here. And this, if you were to look at in Fourier space, this has two modes: one hydrodynamic, this diffusion mode, which we were talking about, and one non-hydrodynamic mode, which is gapped with a gap tau given by tau, 1 over tau. So these are really two sheets of the same quadratic relation with a branch point. And if we decompose in momentum space in x only, then we have and leave t alone. We can easily write down the momentum space trans series for a general solution of this equation. We have a piece coming from the hydrodynamic mode, which is entirely perturbative. So it's only perturbative in epsilon. And a piece coming from a non-hydrodynamic mode. So you can see by the way we've scaled t and x, the non-hydrodynamic mode is necessarily non-perturbative in epsilon. So it appears with the gap tau and a 1 over epsilon squared. So this piece, which comes from the non-hydrodynamic sector, is entirely non-perturbative. And now we can ask, well, what is the corresponding expression in position space? In order to do that, we need to integrate this. We need to do a Fourier integral in K. And that's far from trivial. We need to Fourier transform this expression. And the way we're going to do that is with a saddle point analysis. So for simplicity, we pick some initial data. Again, we're choosing things to make life as simple as possible, to get as far as possible. So here we've got initial data, which is given by a Gaussian. So it's e to the minus x squared over s squared. So s is the width of the Gaussian. And from, once you know this initial data, if I go back a slide, this gets you to determine these a hats and b hats. And then you can do this integral. So the non-hydrodynamic piece of this integral, as an example, is given by the following integration. Integral over k with some prefactor times this term which looks like an action over epsilon squared. The action is given by 3 pieces. The first piece just comes from the initial data. So this is the comes from the Fourier transform of this Gaussian initial data. So there's an s squared appearing in there, the width of the Gaussian. There's a piece coming from the dispersion relation. This is omega t. This is I omega t. And there's a piece coming from the momentum e to the ikx. So this is the action appearing in this sort of saddle point analysis integral. You'll note that this action, and therefore its saddles, depend on all 3 things. It depends on the initial data choice, s. It depends on the space-time point that you look at, x and t. The saddles, there are 3 saddles. There's one at the origin, and there are 2 in K, and there are 2 that are off axis. So if we plot those, what I'm plotting here is the real part of this action that appears in this Fourier integral in complex K plane. These dots are the 3 different saddles of the action. And this left-hand plot is the case where the time is less than some critical time. This critical time is given by the width of the Gaussian. And the right-hand plot is when the time is greater than some critical time. And you can see what happens is that as t approaches the critical time, these 3 saddles coalesce with each other, and then they move off in the imaginary k direction, but t greater than tc. So what this is showing is that there's a Stokes phenomenon as a function of time, space, and initial data in the position space solution to this MIS equation. And the way to see that is, let's say we want our contour to be an integral from this bottom left region to this bottom right region. In the left-hand plot, so these lines that I'm plotting are the steepest descent contours from each of these saddles. So in the left-hand plot, you would take a contour which goes through the middle saddle to the top right, and then a contour which goes through the right saddle to the bottom right. So there are these 2 different contributions. In the right-hand plot, you just have a single contour which goes through one of these saddles. So this leads to a sharp change in the nature of the trans series as a function of time. So for early times, or rather for late times, what you see is you pick up this S minus contribution, and this S minus contribution decays like t squared. So actually you'll see in the actual solution to this problem that there's a distinct change in the behavior of the solution as you cross Tc from something which is decaying like e to the minus t to something which is decaying like e to the minus t squared. And that you can observe. Okay, so let me now summarize. I think I'm a bit over, well, just about on time. So in this talk, we explored large order behavior of the hydrodynamic expansion for both quasi-normal modes, these fluctuations around equilibrium, and the one-point functions of the stress tensor. The quasi-normal modes have a finite radius of convergence, and in many examples, these appear to be set by branch point singularities. One can say that the non-hydrodynamic physics is responsible for that, because if they were not there, there would not be these branch point singularities. So in a linearized setting, the quasi-normal modes and the choice of initial data will determine T mu nu completely, so you need both those things. And this gives you a precise criterion for when the hydrodynamic expansion converges or diverges, right? In terms of when you have enough momentum compared to this branch point scale. And we saw a quick example of how you would try and generalize this to the nonlinear case and this generalizes what people would look at for Bjorken flow, which depends on one parameter, to a PDE with 1+1, including this lattice regulator. So again, I'll point you to Alex's discussion session tomorrow. And in this final part, there was a case study into a trans series and some Stokes phenomenon that occurs in space-time as a function of initial data and the space-time point that you're looking at. So I think some of the things we can learn from these analyses are that, as I mentioned, one source of divergence of the hydrodynamic expansion is really the number of derivatives you have just acting on the data. So if you change the data, you'll change what happens when you act on it with n derivatives, where n is large, and that changes the convergence properties. It's also, I guess, possible that it could be the number of transport coefficients, but certainly not in the linear case, because there are only one or two at each order. So a corollary of this statement is that if you force the solution to be bandwidth limited in some sense, then you can get convergence. So in the linear case, the one way you can do that is you can restrict the data with compact support in momentum space. And that's something you can do because that support does not change with time for a linear theory. In the nonlinear case, you can enforce it by just putting a lattice there. And if you make the lattice coarse enough, then it'll converge. The other example, the other lesson, of course, is that the divergence that you see, for example, in Bjorken flow, is not reliant on the fact that Bjorken flow had all this symmetry. We can still get factorial divergence in cases, or just divergence in cases where there are no symmetries. So in the linear case, we showed this analytically for all of the conformal examples. And in the nonlinear case, we had some numerical example which showed that happened. And finally, I would phrase some central questions, which we can maybe discuss tomorrow. So I think the central question is, does nonlinear continuum hydrodynamics diverge generically? So there are a few different caveats here, nonlinear, continuum, and generic. So the reason I've highlighted those is that, you know, the nonlinear case, if it was linear, we could do this thing where we look at compact K support, but in the nonlinear case, you can't do that because the support will change with time. Continuum stops you putting a lattice there, which gives you convergence, which can give you convergence. So you remove those possibilities. And then you have this issue about whether the theory is generic. So I'm not claiming that we know the answer to this, but some interesting examples which go in this direction, give insight in this direction, are this paper by George and company, where there's a model which converges even though it's completely nonlinear and continuum. So this is an interesting case study. And as we mentioned yesterday in the discussions, there's this large order limit of GR, which gives you a parameter which you can use to set infinitely many transport coefficients to 0, and the theory truncates as exactly second order. So this is a theory which also converges. So there's sort of potential counterexamples to this being true. For practical applications, if this was a divergent theory, we could ask, you know, what is the optimal truncation order? So if you were a practitioner of looking at collisions of heavy ions, you might want to know how many orders in this series do you want to compute to get the best approximation. And can we construct a general trans series for hydrodynamics in the nonlinear generic case? Of course, we looked at some example of a trans series on the last few slides, but this was from MAS when we have one additional non-hydrodynamic mode. In other models like holography, there are infinitely many such modes. So maybe there are infinitely many terms in this trans series. So I think these are also an interesting question to try and answer. Okay, thank you. Sorry, it was a bit rushed at the end, but thank you.
Thank you very much, Ben, for this excellent talk. So we have, I hope, lots of time for questions. And I see that George has raised his hand. Please ask your question, turn on your microphone.
Hi. Yeah, so you already started to uncover a little bit of the connection between this convergence and also what happens in the theory that is causal, right? So you start to worry about that already, and this already showed up. But there another problem that is important is to see also when the theory is stable. So for all these nice results that is done now, considering the collision of these modes and things like that, is it is it any way that you can, is there any way that you can say some, whether there's a connection to stability? Right? Can you also say something about stability in this generic way? It also has to do with the modes, right? So it's just that the imaginary part of the modes. You already made everything complex. You should be able to say something whether or not the omega is in the right complex part.
I don't know how you, so I don't know how to, what you're looking for, but let's say, of course, a condition would be for it to be a sensible theory, you would want, as you say, all the modes in the lower half plane.
Yes.
For real K. For complex K, that you don't need that.
Yeah, for real K, but there has to be a condition, right? So once you already study this in the full complex omega and K plane, the fact that the theory has to be stable has to somehow make a difference. So where does it make a difference?
Yeah, right. So it's tricky to answer that in terms of doing a gradient expansion. That seems to be a very non-trivial. So that's a condition you would have to answer for any finite K, right? You would have to say at a given K, a given real K, here's a set of frequencies. You want them all to be below the axis. Yeah, I have no idea how you would impose that. Going from I guess this is in terms of model constraints on general models. Going from the bottom up, what would you put? What constraints would you put, let's say, on transport coefficients to make sure all these modes are in the lower half plane? Yeah, I don't know if there's a easy answer to that.
I mean, if the theory is truncated, right? If you have an effective theory that you have something truncated, so you have a finite polynomial, then there are general techniques to say that the roots are in the right spot. But of course, you don't have a finite polynomial when you're talking about ADSFT or maybe kinetic theory. So it has to be connected, right?
Yeah, in the case that you discussed, if you truncate and maybe there's all this, as you have explored yourself, there's all this. You can talk about frames as well, truncating, and the relationship with truncating. In that picture I drew at the very beginning, I would think about that as being a candidate microscopic theory. It's a toy model, it's a toy microscopic theory, but okay. And then you were just asking questions about those theories. So of course, those you can answer. I don't know what the significance of answering that question is, because ultimately these sort of models, like these MIS models, are really there just to allow people to do time evolution, I would say. And so you just want something which is well behaved, just to get the job done, rather than from any fundamental physics perspective. Yeah, I don't have anything to add.
Okay.
Okay, so I see that Michael Glinsky has raised his hand. Please go ahead.
Hello. Could you please go back to the slide where you have this model with ABC coefficients? Oh, you just passed it.
Yep.
Okay, this one. So as far as I understand, you recover the coefficient little a-n's and the rest just by comparing with sound mode.
Sound and shear. So for example, so here, okay, so the a-n's is determined entirely by shear.
I see. Okay.
And B and C are determined by a combination of both sound and shear pieces. Okay,
well, problem is the shear mode. I wanted to ask you.
Okay. But exactly. So they're all, there's a one-to-one between these coefficients and the coefficients appearing in this K expansion for both of these things, and the coefficients appearing in A, B, and C.
Well, maybe my more general kind of comment or reservation is there is still kind of scalar or tensor channel which you would not be able to recover correctly here.
I think these are the only excitations you have in the linear case.
No, this is only hydro excitations. You have again some gap.
But this is hydrodynamics, so we only have hydrogen excitations. There aren't any other excitations.
Okay.
I mean, if you truncate this theory, you will find spurious modes. Well, actually, you won't. Yeah, you won't, because we eliminated all the time derivatives.
Yeah, right.
But if you hadn't, you would find spurious modes, and those are I would say not within the realm of applicability of this theory. So I was thinking of this purely as a gradient expansion. And then you only have these two things, sound and shear.
Okay.
Okay, are there any other questions?
Just a thought about some of the aspects that you raise in your the next slide. I think that it was yeah. So so far, all the studies analytical that have been carried out, from which we have learned quite a lot of things, they have symmetries. They are conformal or anything like that. But going beyond than that, I think that we need to start to do that, because we have not really pay attention about what happens, for instance, with the effects of the equation of a state and so on, even in very simple setups. So this is more an observation that perhaps all that structure that you are talking, even in equilibrium backgrounds, can get modified. And even we don't know exactly if all the linear, the growth, the factorial growth that it has been observed in different even toy models might change. So this is more a thought about how general are those conclusions related with the symmetries that we use in those toy models.
Yeah, I mean, going from conformal to non-conformal, I don't imagine will be much of a stretch of this. I think it would probably just go through the same way. But that said, we haven't done it.
That's what I mean. Like when we have, like, for instance, equations of a state that depend on the temperature and so on, it might change. That's my point. My point is more about like how solid those conclusions could be in general, in a little bit more general setup.
Yeah. So I think the minimum step you could do is make it non-conformal. So when you have a conformal theory, the equation of state is fixed for you.
Mm-hmm.
So that's the equation of state we have here, right? The conformal equation of state. Because if you go to non-conformal case, you can that would generalize. Mm-hmm. And yeah, that might be an interesting thing to look at, to try and generalize what we did in that linear calculation.
It's more a suggestion because you say something about the symmetries, and
no. I mean, what I meant was symmetry.
I'm concerned about that. As a person who does a little bit of phenomenology, I am concerned about those implications.
Sure. What I'm referring to when I say symmetries is the symmetries of the solution, not the symmetries of not the microscopic symmetries.
Mm-hmm. Thank you.
Yeah.
Okay. Any further questions from the audience? Well, okay, so maybe if there aren't any more official questions, we will, I suppose, stop recording, and we'll see if that encourages anyone to to speak up and animate this discussion. Thank you again, Ben, very much for this very clear talk, and we'll transit to the last segment then.